All right, let's talk about some of this stuff. This is problem number 1, charging a conducting rod. It's from the electric force homework, I think. Electric charging forces. All right, cool. So this is more of a conceptual one, right? So I'm just going to talk about it here. This problem explores the behavior of a charge on conductors. We will take as an example a long conducting rod suspended by insulating string. It's important that the string is insulated because then charge can't leave through the string. If the string is a conductor, then the charge has a path that it can leave through the string. So we don't want that to happen. Assume the rod is initially electrically neutral. For convenience, we will refer to the left end of the rod as A, right end of the rod as B. All right. So a metal ball given a negative charge and then brought near to end A of the rod, which is in figure 1. You can see it over here. What happens to the end? What happens to end A of the rod when the ball approaches it closely for the first time? So when we bring this charged metal ball close to the rod, right, what happens is all of the positive, I guess I'd say all the negative charges, right, because we want to talk about negative particles moving. All of the negative particles start to move towards the left end of, towards end B. Let me not use left and right. Towards end B of the rod. So we bring the negative ball close. All the particles, the electrons move towards end B of the rod. And when the electrons move towards end B, it leaves an excess of positive charge at end A. And then we have a positive charge very close to a negative charge, and we get an attraction, right? That is called induced attraction, right? We are inducing an attraction in the rod and the metal sphere, or metal ball, by forcing the electrons to go one way and letting the protons stay on the other side. We create a little polarization there, or we induce an attraction. So we try that, right? Correct. Charge is said to be induced by the presence of an electric field of the charged ball, right? No transfer going on there because we haven't actually touched. Now consider what happens when the small ball is repeatedly given a negative charge and then brought into contact with end A of the rod. So if we are touching, just for the first time, right? We touch the metal ball on the uncharged rod, right? It's a neutral rod. Because they want to reach equilibrium, the excess negative charge on the ball is going to transfer into the metal rod, right? It'll transfer over. And if we keep doing that, right, we keep charging the ball negatively, we keep moving it over, we're going to end up putting a lot of negative charge onto the rod. So after a great many contacts with the charged ball, how is the charge on the rod arranged? There's definitely going to be a negative charge. And because we're working with a conductor, right, charging a conductor, right, that charge is going to spread evenly throughout, right? Because the electrons are allowed to move around, that charge is going to spread out and it's going to go evenly on every part of the rod. How does end A of the rod react when the charged ball approaches it after a great many previous contacts with end A? Assume the phrase a great many means the total charge on the rod dominates any charge movement induced by the near presence of the charged ball. So because they're saying we're not going to get an induced charge anymore, right? We're not inducing that, that reaction that we were earlier when it was neutrally charged, we should get a repulsion, right? We would have negative charge on the ball, a whole bunch of negative charge on the rod. That's negative and negative. We should get a repulsion. Boom, 3 for 3. How does end B of the rod react when the charged ball approaches it after a great many previous contacts with end A, right? Basically is saying if we take it around to the other side, right? We take the metal sphere around to the other side. We try it on that side. Because this is a conductor, all the electrons are allowed to move throughout evenly, so we should still get a repulsion on that side as well, right? Because the electrons, the negative charge, has spread out. And there we go. Nailed it. There's problem number 1. Now I just have to figure out how to stop the recording.